It's a theorem! Let A be an m by n matrix, n the solution set of the system Ax equals 0. Then n is a subspace of Rn. Let's go ahead and prove this. Proof. What we really need to start with is we need to check, is this closed under addition, and is it closed under scalar multiplication? So let's check these. Addition. Let u and v be in n. We want to show, WTS is short for want to show. We want to show that u plus v is in n. Well, what do we already know? We know that A times u is equal to 0 because u is in the solution set n of the system Ax equals 0, and the same is true for v. A times v is equal to 0. And like I just said, this is by the definition of n. Therefore, A times u plus v is A times u plus A times v, which is, by what we just saw, 0 plus 0, which is 0. Oh, well that means that u plus v is a solution to the system of equations Ax equals 0. Therefore, u plus v is indeed in n. And therefore, we conclude that n is closed under vector addition. Our next order of business is to prove that the set n is closed under scalar multiplication. Let's do that. Let u be in n and c be in R. We want to show that c times u is also in n. Again, we should use what we know. We know, for the same reason as we did with the addition part, that a times u is 0. Again, that's by the definition of n. Well, therefore, a times c u is equal to, well, c can be brought outside, so it's c times a u, but we know that a times u is 0 from what we just said, and therefore this is c times 0, which is 0. Therefore, c times u is evidently a solution to Ax equals 0, and therefore is in n. And therefore, we can conclude n is closed under scalar multiplication. And finally, since we've shown that it's closed under both addition and multiplication, we conclude, therefore, n is a subspace of Rn. Tombstone. Other than spans, these solution sets to systems of linear equations are the main source of subspaces. But if they're one of the main sources, other than spans, I don't want to keep referring to them as the solution set of Ax equals 0. I want something shorter to write and say. So that's why we make the following definition. Definition. The null space, put a little squiggly under there, of an m by n matrix A is the subspace written null of A of Rn. N consisting of the solutions to the system AX equals 0. But like I said a moment ago, null space of A is just short for saying the solution set of the system of linear equations AX equals 0. Let's look at this thing right here. 1, 2, 3, 4. Since the determinant of A equals -2, which is not 0, A is invertible. But if A is invertible, that means that the solution set to AX equals 0 consists of only the trivial solution. Therefore, by FTIM, the null space of A is just the set consisting of the 0 vector.